The Andromeda Galaxy, also known as Messier 31 M31, or NGC 224, is a spiral galaxy approximately 780 kiloparsecs from Earth. It is the nearest major galaxy to the Milky Way and was often referred to as the Great Andromeda Nebula in older texts. It received its name from the area of the sky in which it appears, the constellation of Andromeda, which was named after the mythological princess Andromeda. Being approximately 220,000 light-years across, Andromeda is the largest galaxy of the local group, which also contains the Milky Way, the Triangulum Galaxy, and about 44 other smaller galaxies. Despite earlier findings that suggested that the Milky Way contains more dark matter and could be the largest in the grouping, the 2006 observations by the Spitzer Space Telescope revealed that Andromeda contains 1 trillion stars, at least twice the number of stars in the Milky Way, which is estimated to be 200 to 400 billion. The mass of the Andromeda Galaxy is estimated to be 1.5 times 1012 solar masses, while the Milky Way is estimated to be 8.5 times 1011 solar masses. In comparison, a 2009 study estimated that the Milky Way and M31 are about equal in mass, while a 2006 study approximated the mass of the Milky Way at 80% of the mass of the Andromeda Galaxy. The Milky Way and Andromeda are expected to collide in 3.75 billion years, eventually merging to form a giant elliptical galaxy or perhaps a large disk galaxy. The apparent magnitude of the Andromeda Galaxy, at 3.4, is among the brightest of the Messier objects, making it visible to the naked eye on moonless nights, even when viewed from areas with moderate light pollution. Observation history. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi described the Andromeda Galaxy in his book of fixed stars as a nebulous smear. Star charts of the period labeled it as the Little Cloud. In 1612, the German astronomer Simon Marius gave an early description of the Andromeda Galaxy based on telescopic observations. In 1764, Charles Messier catalogued Andromeda as object M31 and incorrectly credited Marius as the discoverer despite it being visible to the naked eye. In 1785, the astronomer William Herschel noted a faint reddish hue in the core region of M31. He believed M31 to be the nearest of all the great nebulae, and based on the color and magnitude of the nebula, he incorrectly guessed that it is no more than 2,000 times the distance of Sirius. In 1850, William Parsons, 3rd Earl of Rosse, saw and made the first drawing of Andromeda's spiral structure. In 1864, William Huggins observed the spectrum of M31 and noted that it differs from a gaseous nebula. The spectra of M31 displays a continuum of frequencies, superimposed with dark absorption lines that help identify the chemical composition of an object. M31's spectrum is very similar to the spectra of individual stars, and from this it was deduced that M31 has a stellar nature. In 1885, a supernova was seen in M31, the first and so far only one observed in the galaxy. At the time, M31 was considered to be a nearby object, so the cause was thought to be a much less luminous and unrelated event called a nova, and was named accordingly, Nova 1885. In 1887, Isaac Roberts took the first photographs of M31, which was still commonly thought to be a nebula within our galaxy. Roberts actually mistook M31 and similar spiral nebulae as solar systems being formed. In 1912, Vesto Slipher used spectroscopy spectroscopy to measure the radial velocity of M31 with respect to our solar system, the largest velocity yet measured, at 300 km per second. Island universe. In 1917, Herbert Curtis observed a nova within M31. Searching the photographic record, 11 more novae were discovered. Curtis noticed that these novae were, on average, 10 magnitudes fainter than those that occurred elsewhere in the sky. As a result, he was able to come up with a distance estimate of 500,000 light-years. He became a proponent of the so-called island universes hypothesis, which held that spiral nebulae were actually independent galaxies. In 1920, the great debate between Harlow Shapley and Curtis took place concerning the nature of the Milky Way spiral nebulae and the dimensions of the universe. To support his claim of the Great Andromeda Nebula being, in fact, an external galaxy, Curtis also noted the appearance of dark lanes within Andromeda which resembled the dust clouds in our own galaxy, as well as historical observations of Andromeda's significant Doppler shift. In 1922, Ernst.It presented a method to estimate the distance of M31 using the measured velocities of its stars. His result placed the Andromeda Nebula far outside our galaxy at a distance of about 450,000 parsecs. Edwin Hubble settled the debate in 1925 when he identified extragalactic Cepheid variable stars for the first time on astronomical photos of M31. These were made using the 2.5-meter Hooker telescope, and they enabled the distance of Great Andromeda Nebula to be determined. His measurement demonstrated conclusively that this feature is not a cluster of stars and gas within our own galaxy, but an entirely separate galaxy located a significant distance from the Milky Way. M31 plays an important role in galactic studies, as it is the nearest major galaxy. In 1943, Walter Baade was the first person to resolve stars in the central region of the Andromeda Galaxy. Baade identified two distinct populations of stars based on the metallicity, naming the young, high-velocity stars in the disk type 1 and the older, red stars in the bulge type 2. This nomenclature was subsequently adopted for stars within the Milky Way and elsewhere. Baade also discovered that there were two types of Cepheid variables, which resulted in a doubling of the distance estimate to M31, as well as the remainder of the universe. In 1950, radio emission from the Andromeda Galaxy was detected by Hanbury Brown and Cyril Hazard at Jodrell Bank Observatory. The first radio maps of the galaxy were made in the 1950s by John Baldwin and collaborators at the Cambridge Radio Astronomy Group. The core of the Andromeda Galaxy is called 2C56 in the 2C Radio Astronomy Catalogue. In 2009, the first planet may have been discovered in the Andromeda Galaxy. This was detected using a technique called microlensing, which is caused by the deflection of light by a massive object. General. The estimated distance of the Andromeda Galaxy was doubled in 1953 when it was discovered that there is another, dimmer type of Cepheid. In the 1990s, measurements of both standard red giants as well as red clump stars from the Hippocos satellite measurements were used to calibrate the Cepheid distances. Formation and history. Andromeda was formed roughly 10 billion years ago from the collision and subsequent merger of smaller proto-galaxies, leading to a galaxy smaller than the one we see today. This violent collision formed most of its galactic halo and extended disk, and during that epoch Andromeda's star formation would have been very high, to the point of becoming a luminous infrared galaxy for roughly 100 million years. M31 and the Triangulum Galaxy had a very close passage 2-3 4 billion years ago. This event produced high levels of star formation across the Andromeda Galaxy's disk, even some globular clusters, and disturbed M33's outer disk. Over the past 2 billion years, star formation throughout M31's disk is thought to have decreased to the point of near inactivity. However, such activity had increased relatively recently. There have been interactions with satellite galaxies like M32, M110, or others that have already been absorbed by M31. These interactions have formed structures like Andromeda's giant stellar stream. A merger roughly 100 million years ago is believed to be responsible for a counter-rotating disk of gas found in the center of M31, as well as the presence there of a relatively young stellar population. Recent distance estimate. At least 4 distinct techniques have been used to estimate distances to the Andromeda Galaxy. In 2003, using the infrared surface brightness fluctuations and adjusting for the new period luminosity value of Friedman et al. 2001, and using a metallicity correction of -0.2 magdex-1 in an estimate of 2.57 plus or minus 0.06 million light-years was derived. Using the Cepheid variable method, an estimate of 2.51 plus or minus 0.13 million light-years was reported in 2004. In 2005, Ignacy Ribas and colleagues announced the discovery of an eclipsing binary star in the Andromeda Galaxy. The binary star, designated M31VJ00443799 plus 4,129,236, has 2 luminous and hot blue stars of types O and B. By studying the eclipses of the stars, which occur every 3.54969 days, astronomers were able to measure the sizes. Knowing the sizes and temperatures of the stars, they were able to measure their absolute magnitude. When the visual and absolute magnitudes are known, the distance to the star can be measured. The stars lie at a distance of 2.52 times 10 to the 6 plus or minus 0.14 times 10 to the 6 light years, and the whole Andromeda Galaxy at about 2.5 times 10 to the 6 light years. This new value is in excellent agreement with the previous, independent Cepheid base distance value. M31 is close enough that the tip of the red giant branch method may also be used to estimate its distance. The estimated distance to M31 using this technique in 2005 yielded 2.56 times 10 to the 6 plus or minus 0.08 times 10 to the 6 light years. Averaged together, all these distance estimates give a combined value of 2.54 times 10 to the 6 plus or minus 0.11 times 10 to the 6 light years. And, from this, the diameter of M31 at the widest point is estimated to be 220 plus or minus 3 kly. Applying trigonometry, this is equivalent to an apparent 4.96 degrees angle in the sky. Mass and luminosity estimates. Mass estimates for the Andromeda Galaxy's halo give a value of approximately 1.5 times 1012 m compared to 8 times 1011 m for the Milky Way. This contradicts earlier measurements that seem to indicate that Andromeda and the Milky Way are almost equal in mass. Even so, M31's spheroid actually has a higher stellar density than that of the Milky Way, and its galactic stellar disk is about twice the size of that of the Milky Way. The total stellar mass of Andromeda is estimated to be between 1.1 times 1011 m and 1.5 times 1011 m, with around 30% of that mass in the central bulge, 56% in the disk, and the remaining 14% in the halo. In addition to it, M31's interstellar medium contains contains at least around 7.2 times 109 m in the form of neutral hydrogen. At least 3.4 times 108 m is molecular hydrogen, and 5.4 times 107 m of dust. Studies made with the help of the Hubble Space Telescope and published in 2015 have uncovered a large and massive halo of hot gas enveloping M31. This halo is estimated to contain half the mass of the stars in the Andromeda Galaxy itself. As of May 7, 2015, the halo is about 6 times larger and 1,000 times more massive than previously measured. The nearly invisible halo stretches about 1 million light-years from its host galaxy, halfway to our Milky Way galaxy. Simulations of galaxies indicate the halo formed at the same time as the Andromeda Galaxy. The halo is enriched in elements heavier than hydrogen and helium, formed from supernovae, and its properties are the expected on a galaxy that lies in the green valley of the color magnitude diagram. The supernovae erupt in Andromeda's star-filled disk and eject these heavier elements into space. Over Andromeda's lifetime, nearly half of the heavy elements made by its stars have been ejected far beyond the galaxy's 200,000 light-year diameter stellar disk. Luminosity. M31 appears to have significantly more common stars than the Milky Way, seeming to predominate the old stars with ages and GT 7 times 109 years, and the estimated luminosity of M31 2.6 times 1010 L is about 25% higher than that of our own galaxy. However, the galaxy has a high inclination as seen from Earth, and its interstellar dust absorbs an unknown amount of light, so it is difficult to estimate its actual brightness, and other authors have given other values for the luminosity of the Andromeda Galaxy. An estimation done with the help of Spitzer Space Telescope published in 2010 suggests an absolute magnitude of -20.89, and a total luminosity in that wavelength of 3.64 times 1010 L. The rate of star formation in the Milky Way is much higher, with M31 producing only about 1 solar mass per year compared to 3 to 5 solar masses for the Milky Way. The rate of supernovae in the Milky Way is also double that of M31. This suggests that M31 once experienced a great star formation phase, but is now in a relative state of quiescence, whereas the Milky Way is experiencing more active star formation. Should this continue, the luminosity in the Milky Way may eventually overtake that of M31. According to recent studies, like the Milky Way, the Andromeda Galaxy lies in what in the galaxy color magnitude diagram is known as the Green Valley, a region populated by galaxies in transition from the blue cloud to the red sequence. Star formation activity in Green Valley galaxies is slowing as they run out of star-forming gas in the interstellar medium. In simulated galaxies with similar properties, star formation will typically have been extinguished within about 5 billion years from now, even accounting for the expected short-term increase in the rate of star formation due to the collision between Andromeda and the Milky Way. Structure. Based on its appearance in visible light, the Andromeda Galaxy is classified as an subgalaxy in the de Vogler-Sandage extended classification system of spiral galaxies. However, data from the 2 MASS survey showed that M31 is actually a barred spiral galaxy, like the Milky Way, with the Andromeda's bar oriented along its long axis. In 2005, astronomers used the Keck telescopes to show that the tenuous sprinkle of stars extending outward from the galaxy is actually part of the main disk itself. This means that the spiral disk of stars in M31 is 3 times larger in diameter than previously estimated. This constitutes evidence that there is a vast, extended stellar disk that makes the galaxy more than 220,000 light-years in diameter. Previously, estimates of the Andromeda Galaxy's size ranged from 70,000 to 120,000 light-years across. The galaxy is inclined an estimated 77 degrees relative to the Earth. Analysis of the cross-sectional shape of the galaxy appears to demonstrate a pronounced S-shaped warp, rather than just a flat disk. A possible cause of such a warp could be gravitational interaction with the satellite galaxies near M31. The galaxy M33 could be responsible for some warp in M31's arms, though more precise distances and radial velocities are required. Spectroscopic studies have provided detailed measurements of the rotational velocity of M31 as a function of radial distance from the core. The rotational velocity has a maximum value of 225 km per second at 1,300 light-years from the core, and it has its minimum possibly as low as 50 km per second at 7,000 light-years from the core. Further out, rotational velocity rises out to a radius of 33,000 light-years, where it reaches a peak of 250 km per second. The velocities slowly decline beyond that distance, dropping to around 200 km per second at 80,000 light-years. These velocity measurements imply a concentrated mass of about 6 times 109 m in the nucleus. The total mass of the galaxy increases linearly out to 45,000 light-years, then more slowly beyond that radius. The spiral arms of M31 are outlined by a series of H2 regions, first studied in great detail by Walter Baade and described by him as resembling beads on a string. His studies show 2 spiral arms that appear to be tightly wound, although they are more widely spaced than in our galaxy. His descriptions of the spiral structure as each arm crosses the major axis of M31 are as follows: section pp 1062, section pp 92. Since the Andromeda Galaxy is seen close to edge-on, it is difficult to study its sprawl structure. Rectified images of the galaxy seem to show a fairly normal spiral galaxy, exhibiting 2 continuous trailing arms that are separated from each other by a minimum of about 13,000 light-years and that can be followed outward from a distance of roughly 1,600 light-years from the core. Alternative spiral structures have been proposed, such as a single spiral arm or a flocculent pattern of long, filamentary, and thick spiral arms. The most likely cause of the distortions of the spiral pattern is thought to be interaction with galaxy satellites M32 and M110. This can be seen by the displacement of the neutral hydrogen clouds from the stars. In 1998, images from the European Space Agency Infrared Space Observatory demonstrated that the overall form of the Andromeda Galaxy may be transitioning into a ring galaxy. The gas and dust within M31 is generally formed into several overlapping rings, with a particularly prominent ring formed at a radius of 32,000 light-years from the core, nicknamed by some astronomers the Ring of Fire. This ring is hidden from visible light images of the galaxy because it is composed primarily of coal dust, and most of the star formation that is taking place in M31 is concentrated there. Later studies with the help of the Spitzer Space Telescope showed how Andromeda's spiral structure in the infrared appears to be composed composed of two spiral arms that emerge from a central bar and continue beyond the large ring mentioned above. Those arms, however, are not continuous and have a segmented structure. Close examination of the inner region of M31 with the same telescope also showed a smaller dust ring that is believed to have been caused by the interaction with M32 more than 200 million years ago. Simulations show that the smaller galaxy passed through the disk of the galaxy in Andromeda along the latter's polar axis. This collision stripped more than half the mass from the smaller M32 and created the ring structures in M31. It is the coexistence of the long-known large ring-like feature in the gas of Messier 31, together with this newly discovered inner ring-like structure offset from the barycenter, that suggested a nearly head-on collision with the satellite M32, a milder version of the cartwheel encounter. Studies of the extended halo of M31 show that it is roughly comparable to that of the Milky Way, with stars in the halo being generally metal-poor, and increasingly so with greater distance. This evidence indicates that the two galaxies have followed similar evolutionary paths. They are likely to have accreted and assimilated about 100 to 200 low-mass galaxies during the past 12 billion years. The stars in the extended halos of M31 and the Milky Way may extend nearly one-third the distance separating the two galaxies. Nucleus. M31 is known to harbor a dense and compact star cluster at its very center. In a large telescope, it creates a visual impression of a star embedded in the more diffuse surrounding bulge. The luminosity of the nucleus is in excess of the most luminous globular clusters. In 1991, Todd R. Lauer used WFPC, then on board the Hubble Space Telescope, to image M31's inner nucleus. The nucleus consists of two concentrations separated by 1.5 parsecs. The brighter concentration, designated as P1, is offset from the center of the galaxy. The dimmer concentration, P2, falls at the true center of the galaxy and contains a black hole measured at 3 to 5 times 107 m in 1993, and at 1.1 to 2.3 times 108 m in 2005. The velocity dispersion of material around it is measured to be approximately equals 160 km per second. Scott Tremaine has proposed that the observed double nucleus could be explained if P1 is the projection of a disk of stars in an eccentric orbit around the central black hole. The eccentricity is such that stars linger at the orbital apocenter, creating a concentration of stars. P2 also contains a compact disk of hot, spectral Class A stars. The A stars are not evident in radar filters, but in blue and ultraviolet light they dominate the nucleus, causing P2 to appear more prominent than P1. While at the initial time of its discovery it was hypothesized that the brighter portion of the double nucleus is the remnant of a small galaxy, cannibalized by M31. This is no longer considered a viable explanation, largely because such a nucleus would have an exceedingly short lifetime due to tidal disruption by the central black hole. While this could be partially resolved if P1 had its own black hole to stabilize it, the distribution of stars in P1 does not suggest that there is a black hole at its center. Satellites. Like the Milky Way, the Andromeda Galaxy has satellite galaxies, consisting of 14 known dwarf galaxies. The best known and most readily observed satellite galaxies are M32 and M110. Based on current evidence, it appears that M32 underwent a close encounter with M31 in the past. M32 may once have been a larger galaxy that had its stellar disk removed by M31, and underwent a sharp increase of star formation in the core region, which lasted until the relatively recent past. M110 also appears to be interacting with M31, and astronomers have found in the halo of M31 a stream of metal-rich stars that appear to have been stripped from these satellite galaxies. M110 does contain a dusty lane, which may indicate recent or ongoing star formation. In 2006, it was discovered that 9 of the satellite galaxies lie in a plane that intersects the core of the Andromeda Galaxy. They are not randomly arranged as would be expected from independent interactions. This may indicate a common tidal origin for the satellite's collision with the Milky Way. The Andromeda Galaxy is approaching the Milky Way at about 110 kilometers per second. It has been measured approaching relative to our Sun at around 300 kilometers per second as the Sun orbits around the center of our galaxy at a speed of approximately 225 kilometers per second. This makes Andromeda one of about 100 blue-shifted galaxies that we observe. Andromeda's tangential or sideways velocity with respect to the Milky Way is relatively much smaller than the approaching velocity, and therefore it is expected to directly collide with the Milky Way in about 4 billion years. A likely outcome of the collision is that the galaxies will merge to form a giant elliptical galaxy, or perhaps even a large disk galaxy. Such events are frequent among the galaxies in galaxy groups. The fate of the Earth and the Solar System in the event of a collision is currently unknown. Before the galaxies merge, there is a small chance that the Solar System could be ejected from the Milky Way or join M31.